Hi everyone. So this lesson is going to be on Ksp. Okay, Ksp. So we see the big capital K. So remember the big capital K here once again is the equilibrium constant, and then Sp. This time the Sp is going to stand for solubility product. So remember in the neutralization reactions where we had acid plus base gives you salt and water? So now we're going to be talking about those salts or those ionic compounds. So not all ionic compounds are very soluble in water. So now we're going to do what is called equilibrium for insoluble ionic compounds or insoluble salts. So the first example that I want to go over with you is, let's take a look at nickel sulfide. Okay, nickel sulfide is not very soluble in water, so we will use a double-headed arrow and then show what it looks like if it were to dissolve. Okay, it will separate a very small extent into ions. All right, so notice here it starts off as a solid, and then we are showing what it looks like when it dissolves in water. Okay, so the ions would be aqueous. Then if we were to write the equilibrium expression or the Ksp expression for this, it's the same idea. Okay, the coefficient would become the power, products over reactants. But notice that our reactant is a solid. And remember, we do not include solids into our equilibrium expression. So then if you can remember that Sp stands for solubility product, then for Ksp, we are only including the product side only because the reactant is a solid. Okay, and then the Ksp value for this is 4 times 10, so 4 times 10 to the negative 20. See how small that exponent is to the negative 20. So that is telling us that it does not separate into ions very much at all. All right, so a common question would be, what is the concentration of the nickel ion? Okay, that is a very, very common question. All right, so let's go ahead and proceed and try and solve for this. So let's move this up. There we go. Okay, so now I have more room. All right, so let's go ahead and mathematically solve for this problem. So if we're solving for nickel, so nickel would be our X. Okay, now let's take a look at the mole-to-mole ratios. All right, so the coefficient is 1 and the coefficient is 1 here. So if nickel is X, then what would the sulfide be? The sulfide would also be X, right? Because it separates into a 1-to-1 ratio, so therefore those two would be the same. And then the Ksp value is already provided there. All right, so then we can just solve. So x times x is x squared, so that equals the 4 times 10 to the negative 20. Okay, so now we're going to solve for x, so square root both sides, right? And then you can practice putting that into your calculator, or this particular one, you can probably do this one in your head, and you should get 2 times 10 to the negative 10. Since we were solving for concentration, then we would put the units of molarity there. Okay, so then that would be the nickel concentration. All right, let's do another one. Okay, so for this one, let's do PBS as a solid. Okay, and then when this separates into its ions, that would be aqueous. And then sulfide, aqueous. Okay, I want you, for this one, to solve for the concentration. So let's see, what is the concentration of the lead ion? And let me give you the Ksp value for PBS. So the Ksp value for PBS is 3 times 10 to the negative 28. Okay, so go ahead and solve for this one by yourself. So obviously first you should set up your Ksp expression and then go ahead and mathematically solve for it. Okay, so you should pause it, try it on your own, and then play the video to check your answer. Alright, so then the Ksp expression, products only. Okay, so the Ksp is given to us, 3 times 10 to the negative 28. Alright, so now let's see if we can mathematically solve. So the coefficient here is 1, right? So then we'll say that is x, right? So if this is x, then what's the sulfide going to be? So it's a 1-to-1 ratio. So then sulfide would also be x, right? So it's x times x, right? Which is x squared. Alright, then solve for x, square root both sides. And then if you solve for this correctly, you should get 1.7 times 10 to the negative, oops, that doesn't look right, 14 molarity. Okay, 1.7 times 10 to the negative 14 molarity. So that would be the concentration for both the lead ion and the sulfide ion, because both of them are represented by X. Okay, so now I'm going to ask you a question that relates to both of those that we just solved for. Alright, so if we compare, so the first one we did was the nickel, right? That nickel concentration, if you look back on your notes, it should have been, let me see if I can find it. Okay, so 2 times 10 to the negative 10 molarity, right? And then the lead concentration was 1.7 times 10 to the negative 14 molarity. All right, so now here is a question relating to both of those. Which one is more soluble? Okay, so which one dissolves more in water? The nickel compound or the lead compound? So take a look at their concentrations. 2 times 10 to the negative 10, and this is to the negative 14. Well, which one is a higher concentration, negative 10 or negative 14? Negative 10, right? That one's a higher concentration. So the nickel, right, is the one that is more soluble. All right? And so also, you can, if you compare their Ksp values, so those are their concentrations that we took, that we were comparing. But it's also related to their Ksp values. So if we take a look at their Ksp values, the nickel sulfide was 4 times 10 to the negative 20, and the lead sulfide was 3 times 10 to the negative 28. Okay, so you can also just look at their Ksp values, negative 20 versus negative 28. So that's why that one was more soluble, because it has a larger Ksp value. Okay, because it has a larger Ksp value. So then therefore we can say as Ksp increases, solubility increases. Okay, so as the Ksp increases, the solubility increases. Now, both of those examples were involving if it was a 1-to-1 ratio. Okay, now some people will ask me, well, what if it is not a 1-to-1 ratio? How do we solve that? Okay, so now let's do something that is not a 1-to-1. All right, so this would be a more advanced type of problem. On the test, I will give you something that is only a 1-to-1 ratio. Something that is not 1-to-1 would be like a bonus question or a really good extra credit question on the test. Okay, so the example for this one, we're going to take a look at magnesium hydroxide, which is a weak base, Okay, so we use a double-headed arrow. It does not dissolve that much in water. So when we write out this Ksp expression, okay, products only, but then don't forget the coefficient becomes the power. So this hydroxide is going to be squared. Okay, so that hydroxide is going to be squared. These Ksp values can be found like in a textbook in the appendix or something. So the Ksp value for the magnesium hydroxide is 7.1 times 10 to the negative 12. All right, so now let's do our math. Let's do our algebra and what we want to solve for. So our question will be, what is the magnesium concentration? Okay, let's find the magnesium concentration and let's find the hydroxide concentration. Okay, so let's find both of those. All right, let's take a look here. The coefficient here is a 1. Okay, so the magnesium is going to be X. Okay, magnesium is going to be X. Then this coefficient here is 2, right? So if this is 1x, this is twice as much. So then what do you think the hydroxide would be? The hydroxide would be represented as 2x. Okay? So then we would plug that into our expression here. All right? So then we said that the magnesium is X and that the hydroxide is 2x. Okay, so you see how I got that here because we said that was 2x. So I plugged that into there. All right, so then what this looks like is, it looks like this. So this is x, and then this is 2x, but don't forget that whole thing is squared. So 2x times 2x is 4x squared, right? So then this becomes 4x cubed, all right? 4x cubed. So now we are going to solve for x. Okay, so you divide by 4 on both sides, all right? And then you're going to cube root, okay? Then you're going to cube root both sides too. All right, so this is where you have to take a look at your calculator and how you would cube root something. I like to put in my cube root because I use like a graphing calculator. You usually see like a little caret key. So whatever number it is that you want to cube root, you could use then the little caret key, and then in parentheses, I put 1/3, okay? Or if you wanted to fourth root something, then it'd be 1/4. Or if you wanted to fifth root something, it'd be 1/5. All right? Okay, so put this into your calculator. And in the end, though, when you solve for x, the x should equal 1.2 times 10 to the negative 4. Okay? That is what you should get for x. All right, so then we go back. Okay, so if this is x, x represents magnesium. So therefore, that is the concentration for the magnesium. 1.2 times 10 to the negative 4 molarity. Then we also want to solve for the hydroxide. Well, the hydroxide is 2x. So it'd be 2 times that value for the hydroxide, right? So multiply that by 2, and then that's how you should get 2.4 times 10 to the negative 4 molarity. All right, so that is how you would do something that is not a 1-to-1 ratio. All right, the very last thing I want to go over with you is this concept called the common ion effect. Okay, common ion effect. All right, so here we go, common ion effect. All right, common ion effect here. Let me just give you like one example. I'll give you a couple examples of common ion effect, but just in general and as how this relates to neutralization in this whole chapter and everything else. Okay, so imagine this is your stomach, okay? And you know that your stomach is very acidic. All right, so that means you have a lot of acid in your stomach. So I'm putting a whole bunch of H pluses to represent the acid in your stomach. Now, if you get an upset stomach, sometimes that might mean you have like a lot of acid in your stomach. So it's making you have like a tummy ache. So you got way too much acid here. So some things that you can take to kind of help your stomach ache, you can take like Tums, milk and magnesia, some of that stuff. And what those things contain, they contain a base. Okay, they contain a base. So then I'm going to add in hydroxide here. All right, so what is this going to make? You get H plus and OH minus in here. What does that make? So we can group those together. What does that make when those combine? Right? That makes water. All right, so notice by adding in a base to your very, very, very overly acidic stomach, it is neutralizing, taking away, or the hydroxide's combining with the H plus to make water. It's trying to neutralize the acid, some of the acid in your stomach. Okay, and then after you take that, since it's producing some water, then you probably got to go pee a lot after you take some of that stuff. So that's one way that the common ion effect could work. You have to take a look at what's being added, what's being combined, what can be made, and then therefore how would this affect equilibrium. All right? Okay, so that's like one example of common ion effect. Let me go over another one. Something that you would probably deal with a lot more. All right, so let's raise this up. Okay, so let's see. Let me give you this example, barium sulfate. All right, barium sulfate is not very soluble at all, and this is something that the doctors might make you take if you have like digestive problems and they kind of want to see what's going on in your intestines. So they will make you drink this stuff that does not taste very good at all. Okay, in your so that when they take the x-ray, it'll show up on the x-ray and they can see what's going on in your intestines. But the bad thing about barium sulfate, okay, yeah, it doesn't separate very much into ions, but barium ions, if you have barium ions in your system, that's very toxic, okay, and you can die if you get too much barium in your system. So usually in the barium sulfate solution, they will mix sodium sulfate with it. Sodium sulfate is very soluble in water. All right, so they're going to add some sodium sulfate to the barium sulfate mixture. Now, what do these two equations here have in common? Okay, so take a look at them. And remember, this concept is called the common ion effect. So which ion do they have in common? Well, if you take a look, they both have sulfate in common. Okay, so by adding in the sodium sulfate, you're actually increasing, therefore, the concentration of sulfate ions. Okay, so you're adding in more sulfate. So how is that going to affect the equilibrium? Well, if you add more sulfate, it's going to shift the equilibrium away from itself, right? Remember, add away. So add away. So it's going to cause the equilibrium to shift to the left. Okay? Therefore, increasing the concentration of the barium sulfate and minimizing the ion concentration here of the barium that is toxic for you. Okay? So that is one of the applications of common ion effect that we would see in the real world. All right? Okay, so that is everything for chapter 21, and I will see you later. Bye.